In this video, I will introduce Ampere's law and I will give you an example of how we apply it. Let's say we have some wires in space carrying some currents, I1, I2, and let's pick a path that goes around them. It's important that this path is closed, so we always end up where we started. Somewhere along the path, we have magnetic field, which we don't know much about it. Let's say here's the vector B, and we will work with the infinitesimal length along the path dl. Here we'll have also to keep track of the angle theta between the two vectors b and dl. Ampere's law says that as you walk around that path and you calculate the product of the magnitude of the magnetic field B and the magnitude of this infinitesimal length dl and cosine of the angle between the two, in other words, you keep track of their vector dot product, b dot dl. Once you complete the path and you end up where you started, the left-hand side, no matter what shape you chose for your path and no matter what the wires were and how they went, the value of it will always be equal to mu naught times the enclosed currents. So here mu naught has a value of 4 pi times 10 to the minus 7, and it's the permeability of free space or vacuum, and I enclosed is simply the amount of current around which I just walked. In this case, it will be I1 plus I2. Generally speaking, Ampere's law will give you some information about that magnetic field created by those currents. But look at the picture. It's not a pretty picture. There are no good patterns, and so ultimately going there and brute forcing it will end up with a very unpleasant integral on the left side. And you might as well use the Biot and Savart law, which is the most general and powerful law when it comes to calculating the magnetic field. In either case, it's not going to be a pleasant calculation. So let me show you when Ampere's law is really used. If we have some symmetry or we already know some information about our situation, Ampere's law could be actually a pretty elegant and awesome way to get to the value of the magnetic field. Imagine you have a straight wire, and again we'll take that wire very long, so we can imagine it's almost infinitely long. We will pick also the path around the wire to be a circle with the radius r. Here's my infinitesimal length dl. And the magnetic field B, in this case, I know how it looks. It takes simply running to the lab and taking a compass needle and going around a wire, and you'll find out very quickly that the magnetic field really is going around the wire in a pattern that is always parallel to the tangent of that circle. In this case, the angle between dl and B is really 0, and so now I can apply Ampere's law. The left-hand side, where the dot product is, simplifies very quickly, because instead of doing b dot dl, I can just work with the magnitude of the vectors b and dl, and cosine of the angle between the two will be cosine of 0, which is 1. Also, we know something about the magnetic field of a straight wire carrying a current I. We know that field cannot depend on anything but the distance, how far you are from the wire. So I don't need to worry about that magnetic field inside the integral. I can take it out, and the integral simplifies simply to an integral along dl as I circle once along my path. That integral, of course, is going to have a value of 2 pi r, and so here we arrived at our familiar expression for the magnetic field of a wire at a distance r from it.